magnetized warmness matter. Okay, so today I'll talk about how to have magnetized warmness matter experiments for the first time. And what I present today will be mostly based on simulations we had for that purpose. I will first walk you through the design we had, which we call hohlraum, but it's different from the usual fusion hohlraums in the way that we cut it. And then I will talk about how we had simulation data for that to support that experimental design. And then finally, I will talk about the experiment proposals we have, and one of them is actually coming in November. Before I start, I would like to thank the team I work with and also our funding resources. None of this work would be possible without their help, so I really appreciate all that. And also special thanks to my group, Extreme Safe Physics Laboratory at UFR, and also Experimental Division at the Experimental Division I work with, Innovative Concepts Group at LLE. And I want to first start with the gist of everything. So magnetized resonance matter can be studied experimentally for the first time. But if we want to complicate it a little bit, it actually is because we can reach kilotesla or the magnetic fields in an open geometry, which allows introduction of other laser beams to create and diagnose a resonance matter sample. And I will show why it could be possible with some MHD simulation data. But before that, I would like to mention why we are interested in that. So I will first walk you through a motivation, and then I will explain the design to you, and then I will show you the simulation results, and finally some experiments proposals. I said experiments, but I don't have experimental data yet. These are just proposals and some experimental designs to initiate this experimental campaign. So first, motivation. So what is warmness matter, and why are we interested in that? Warmness matter is warm and dense, just like the name implies. It's warm. So the temperature is around the order of 1 eV, which is like 11,000 Kelvin. And density is around the order of 1 gram per centimeter cubed, which is like a solid density. But as you can see from this plot too, it's right in between plasma and condensed matter regimes, which means it's even more complicated to understand compared to these two, because just like in plasma, we need to consider thermodynamics, and just like in condensed matter, we need to also consider the quantum effects that will be present. So it's a rather complicated state to understand. But it's still relevant to what we see in astrophysics. For instance, to white dwarfs or interiors of exoplanets, we expect to see warmness matter. And also in fusion setups, we see a lot of transitions from solid to plasma, and during that transition, we see a lot of warmness matter. So that's why it's of interest to both astrophysics and fusion communities. However, we also expect this extreme state of matter to coexist with extreme magnetic field strengths. For instance, for white dwarfs, we expect to see 10 to the 7 Gauss of magnetic fields to coexist with the warmness matter state. And for fusion setups, we generally, there are also magnetic confinement. So we also, in that case, get help from kilotesla order magnetic fields. Again, 10 to the 7 Gauss is 1 kilotesla. So it coexists with kilotesla order magnetic fields already, and we know that. But when I say magnetized warmness matter, I'm not only talking about the warmness matter coexisting with magnetic fields. I'm also talking about it being magnetized. And how can we tell that? We can tell that by just a simple comparison. This is just to estimate the order of magnitude that we need. We can compare the cyclotron frequency of the electrons that will be present in the system with the collisional frequencies that we will see in warmness matter. In that case, I'm comparing it to the electron-ion collisional frequency in the warmness matter, which is based on this paper that I cite here, which considers the quantum effect. And this is like the only work that I could find to compare to the collisional frequency. So even the theory work on warmness matter is rather limited. And so this is from that. And when we compare these two, so that means we should at least have one cyclotron frequency of the electrons to be present compared to the collisions. And from that, we can estimate an order of magnitude kilotesla too. So kilotesla, if we compare it to what we feel on the surface of the Earth, it's very small because we only have 0.5 Gauss, and this is 10 to the 7 Gauss. So compared to that, it's really strong. But in the lab, it's actually not impossible to get because there are already existing methods to create kilotesla magnetic fields. One way to do that in solid state physics, people literally explode things. And this is in a very small volume, and they have they really charge it to really strong voltages, and then they have the such up explode, and they can create really strong magnetic fields for very small volume. This is from an experiment in Japan that I just like the gift for. But this is not relevant for our kind of physics because we're interested in studying the inner structure of a material under really strong magnetic fields. And we need to create and diagnose the sample so it doesn't work for our case. The other way in plasma physics that is more related to us is people start with really strong people start with what they can achieve to begin with as a seed field. This is probably on the order of 10 teslas. And then they have a converging geometry and they point their laser beams to the outer surface of that target. And that ablated plasma that is moving inwards, which is of high density and low temperature, can compress the magnetic field. And this is how we have the laser-driven magnetic flux compression. This is a nice and working way that we know is relevant, but it doesn't work for our purposes because for our case, we need really subcritical density plasmas. What I mean by that is for creating and studying our warm-mass matter sample, we need an open geometry so that another laser beam can be introduced. So if we have high density material, we cannot point a laser beam there because it's above the critical density. We know that laser will not be able to pass through all that plasma, so it doesn't work. That's why.
So critical density is just when the plasma frequency is above the laser frequency or below.
Yeah. That's why we needed to come up with an alternative approach to the existing method so that we can create and diagnose our sample. So for that, I will be now talking about the design and why we call it a hohlraum, and that's why I highlight it here. And let's brainstorm for that together too. Again, just like in the previous setup we have seen, we will need to start with a converging geometry and a seed magnetic field. In that case, let's assume that we are looking at its cross-section, and we place our sample again at the very center of it. And we have an initially applied axial magnetic field line pointing inwards to this page. And in this case, we can also provide the initial magnetic field through MyFET's coils that we have. MyFET's is a pulse-powered device, actually, a tiny pulse-powered device that can provide really strong currents through these coils to give the initial magnetic field strength. I will talk about that a little bit later, too. But for our purposes, if you want to study magnetized warm-mass matter sample, and at first we focused on phase transitions in magnetized warm-mass matter, which means we needed a diagnostic to probe that. And in that case, we need a diagnostic like a PX artifact, which stands for powder X-ray diffraction image plate. And it's a rather big diagnostic, which gets help from X-ray backscattering, those X-rays that pass through the sample, and we can, through these image plates, can see what's happening inside it. So we need to allocate some space for that, and that's why we cut the setup in half, and that's why it's different from the usual hohlraums, which are normally the usual hohlraum in fusion community is just you have a cylinder, you cut in the radial plane, but we cut it like this, so it's different. That's why.
Is it open on the right side, or is it?
It's still closed.
It's still closed. Okay.
So we can wrap the coils around it.
And I'm sorry, this question is a little out of order, but what's the advantage of compressing the magnetic field with the plasma?
The advantage, I'm actually coming to that.
Okay.
So we do just one change in our setup, and that's, I think, very convenient, because as opposed to having the laser beams from outside, we point it to inside. So I'll name these compression beams, which will be used to compress the initial magnetic field line. And this way, when we just change the laser beam direction, the ablated plasma is of lower density, but it's still of high temperature. So it means it still carries that high pressure with it, and it can still compress the magnetic field lines. So coming back to your question, could you repeat your question, please?
Oh, just what's the advantage of given the hohlraum is already enclosing the plasma, what's the advantage of compressing the magnetic field lines with it?
Because now we have subcritical density plasma, and that means we can introduce a heating beam to create the sample. And another advantage that I will come into is the fact that we can have the MyFET's coil very close to our target, because now the laser beams are not on our way. So that will give us also a stronger magnetic field to start with. So
is this hohlraum, is this purely for experimental, like diagnostic technique, or are you actually proposing this eventually for like a fusion power source?
Not as a fusion process, but I don't. In the fusion case, they would need higher densities too. It's more of a magnetized HEDP community interest as a pure science interest or astrophysics interest. And this way we can introduce the heating beam, which would create the sample itself. And in order to help with the densities further, to make sure that this heating beam can pass through it, we also introduce an obstacle right around it to help further with the densities. So that's the cross section of it. But if we look at the 3D model, it will actually look like this. So we have the compression beams from the openings from the up and down, and the magnet coil can now be wrapped around the target directly. So we can now start with a 50 Tesla magnetic field as opposed to 10 or 20 Tesla. And we can also see how the heating beam can pass through this conical opening there to create the sample that which will be at the back of it, and we can see it right now. So that's the idea. But in order to see if this will work, we would need to simulate it to see if it really agrees with our intuition. And now I will be talking about the simulations.
Is this like a centimeter scale device?
Millimeter scale. And the first two questions to test the feasibility of this design is one, can we really reach kilotesla order magnetic fields at the location of the sample? So that's the first question. And second question is, are the densities really subcritical? That critical density I calculated for 9 times 10 to the 27 per meter cube. Everything in PERSEUS is an MKS except for temperature, by the way, which is an EB. So I will stick to MKS units. Are the densities in between the heating beam and the sample really subcritical? So do we see really densities below this value? These are the two main questions, the first feasibility of the design. And for that purpose, MHD simulations, magnetohydrodynamics simulations are enough because we're only interested in the behavior of the plasma and the magnetic field compression. So MHD combines the Maxwell's equations with Navier-Stokes equations, and the code I use for that purpose is PERSEUS, which is an extended MHD code, which means it considers generalized Ohm's law with the resistivity in the setup too, but it doesn't include the laser beam as a laser beam. It introduces it as a power density term. So I don't simulate how the sample is behaving. I'm only looking at how the plasma is being compressed and how it can compress the magnetic field mass. So for that, we start with actually the cross section that I showed you earlier. So we have the hohlraum, the conical target, and the sample at the center. We start with an initial 50 Tesla magnetic field all through the grid. We have closed boundary conditions on everywhere except for the right. On the right, we have open boundary conditions, but I also include that the part that closes this B shape here. So there is actually a little bit of an opening here to make sure the magnetic field is not artificially compressed because of the closed boundary there. And another information here. Oh yes, I simulated for 20 omega beams, so 10 kilojoule of energy.
So those are just laser imprints, or are they really tailored institutes that developed on that?
Do you mean the contours or the blue ones?
Yeah, so I think, yeah, so the cone is there, right? But now I see these plumes coming out, these plumes.
Yes.
Are they just from laser imprints, or are they some kind of instability?
I think there are probably some instability because laser imprint, I just give it as a uniform laser
So you give it the
power
uniform.
density.
I see. So it's uniform initially. So what seeds at the initial like perturbation?
I don't, okay, we just, I think, multiply the density with some 1 point something, like a multiplier, to give some impurity to our sample.
So in your simulation, you put a fluctuations on the test.
I don't really put a fluctuation, but I'm trying to remember. We have this, random number generator there, but I think it was disabled. So it's just a density term multiplied with a little bit of a factor there to introduce a little bit of impurity there.
So what's the impurity for?
Because target wouldn't be perfect. Right now for CH, and we simulate it as carbon, but when we produce the target, really, it wouldn't be perfect.
I see. So if you wait for the movie to play again, so there are initially like two jets coming out, and the location of the jet is that corresponds to your impurity.
It's more like a computational instability, I think.
It's more of a computational thing. I see. So why isn't there 5 jets? Why are 2, for example?
What do you mean by 2 jets? It will start again.
Right.
Yes.
Right. So see if you look at the upper half, right? So now there's some wiggles growing, and then there are 2 things that are protruding, right? So why are there 2 of them, not 5 of them?
I think that's computational because this is this grid space is in Cartesian, but the geometry is cylindrical. So I think that XY.
Okay, so there's some grid scale. Okay, I see. Okay.
And now that I actually make sure in my mind that the random number generator was deactivated, so the impurity is not there.
Okay.
That's purely computational. Should be
okay.
Yes, it's been some time since I simulated it. So now actually, if we freeze this picture, what you see here is a 2D simulation results from PERSEUS, and the main questions can be answered actually with a line out. So we can already see in the 2D that at the center location from the contours, the magnetic field strength is above 1 kilotesla. But from the line out that we take along this green line, we can see that the densities which are shown in blue are below the critical density that is shown in yellow. And this is at time 3.9 nanoseconds. And the pulse is 2 nanosecond square pulse, which we can easily have at omega. So after that 2 nanosecond pulse, approximately 2 nanoseconds later, once the pulse is done, we can see that the magnetic field is above 1 kilotesla at the sample location, and the density is in between the heating beam and the sample is below the critical density. So that gives us hope that this kind of a design can actually really work for magnetized warmness matter setup.
So the critical density is for 1 omega, 3 omega?
One omega.
For 1 omega beam. I see. So, and that's because you want to have the 1 omega beam to heat the sample.
Yes.
So the 3 omega beam would be like pretty low density plasma.
What do you mean? Do you mean
the laser frequency? It's a 3 omega beam. It's way above the.
It's just the usual 1 omega beam.
I see. I see.
Because I'm not even sure if we can do that on omega. I think we can do that on EP, but
yeah, on EP you have 1 omega,
4 omega,
3 omega, and you have 4 omega probe, right? So in principle, this is below critical for 4 omega probe. So you could do the Faraday rotation for the 4 omega probe just from this plasma as a way to measure the heat field.
That's sort of future, yes. Maybe. A question mark.
Okay.
But who mentioned this? Was that you? No, I think I'm so bad with names. But the professor I talked to him. He said he probably doesn't. Or was that you who said I heard this from someone today with high where the oh no, you said this.
Yeah, so if you put the material like a glass that has a Faraday rotation thing, that will not work. But you have a magnetized plasma. If you just shoot laser through this plasma, it will rotate.
Yeah, and then you said it would be opaque.
Yeah, I thought you wanted to put a piece of material there. That will have problem. But if you just shoot through the plasma itself, and if you are below critical density, if you shoot the 4 omega beam, then you can have a Faraday rotation measurement from the plasma itself.
Yeah.
No other materials.
That could be interesting. That could be a way. Because yes, that's an active concern for what I will talk about when I come to the experiment, which is actually now. Oh, no, not now. But before I come to that, the experimental side and what are the existing challenges right now, I want to also mention that in our code PERSEUS, we don't have Nernst effect, which we would expect normally for the compressed magnetic fields. What people see is that Nernst generally advects that because of the strong density gradients. But in our case, it's also in our favor. Although PERSEUS does not include that in the simulation, I calculated it for that and plotted based on the values that the simulation reports. So in that case, that's another advantage of our design, because the existing designs, the magnetic fields get advected with the Nernst. But in our case, that density gradient is in the opposite direction. So it's even good for us, but it
So
doesn't
what's
change.
your density profile look like?
You can actually already see it here. This is in log scale.
So that's the blue thing is density.
Yes.
Oh, I see.
More blue it is, more dense it is. So there will be some like density gradients there.
So how about the temperature profile?
Temperature, temperatures around the close to the sample, it's really hot, like 100 EV.
Yes. So NERSC usually goes with the heat flow. Right, so it's
Temp density.
yeah, heat and density. So on your next slides, the green thing is what?
That's
NERSC
the,
velocity over what?
over the flow velocity.
Flow velocity.
That
And
is-
your is 10 to the 10.
It's log scale, so it's very small.
Minus 10.
Yes.
Oh, I see. I see.
Very, very small, not even important.
Oh, I see. I see.
That's
Because you have a supersonic flow.
Mhm.
The NERSC is subsonic, so it cannot be as large.
Yes. And as I said, also the gradients are also helping with the changes that we have too. So that's not something to be concerned for. And now I will talk about how we could start an experimental campaign for magnetized Romanesque matter experiments in the hope that this setup can come into reality. So for that, first one, this is for EP. And maybe I should have included an introductory slide for LLE, but LLE has two chambers. One of them is omega with 60 beams and in total 30 kilojoules of energy. And the other one is EP, which has 4 beams, but these 4 beams are identical to the NIF's 198 beams. So 4 of them. So it can be scaled to NIF very easily, and people also come and do such experiments. In our case, we want to start the experimental campaign simple because there are 2 layers to our experimental design, and it's already hard to measure a magnetic field and also to create a magnetized Romanesque matter sample. That's why if this very first step is an experiment, we want to first measure the magnetic field compression ratio, or if we are lucky, the magnetic field strength, the final magnetic field strength, which would be farther.
In what sense are 4 beams here equivalent to NIF's 160?
NIF's 190.
Or 90?
But yes, they're exactly the same. So each beam is separately following its own beam line.
So each single beam is equivalent to one of the NIF's beam. Got it.
Yes, maybe I should have said it that way. Yes. And normally in omega, for instance, they generate that one big laser beam, and then it's divided to 60 beam, and it's pointed to the center of it. This one, the advantage of the EP one is one, we have less beams to deal with, less complicated. So that's why we want to start with EP. And two, we can still have proton radiography with this setup because on EP, we also can use one of these, actually 2 of these beams, but one of these beams as a backlighter with a short pulse beam and generates TNSA protons. So what you do is you have a tantalum filter, you have a short pulse beam that comes through it, and it accelerates these protons, and once they pass through the mesh, if there's no magnetic field, it just looks like this. But if you let them pass through an electric and magnetic field that is present in your setup, then you can see how your mesh gets warped and also rotated. And you can tell from this how much magnetic field you have. So this is the synthetic proton radiography image, but you can see that the design is a rather simple one with just a cylindrical target and some solenoid-shaped coil, Magnetized coil wrapped around it. And you can also see the PERSEUS simulation results for that, showing us what magnetic field we expect, what kind of densities we expect. And for that, we expect the magnetic field at the center to be around 100 Tesla when we start at 50 Tesla. And we will have a shut day for this around sometime in November. There's a question? Is there a question?
I don't think so.
Okay.
Okay, so what constrains the thickness of the cylinder target?
I kind of related to the earlier design. And in the earlier design, if it's too thick, the subcritical density gets a little bit risky. Like you can.
So if it's too thick, but if it so in your original design, at the end of it, you burned all the materials off.
Mhm.
And at that point, do you turn off your laser?
What do you mean by burned everything off?
So it's meaning there's no material left, right? So you have a cylinder, right? So as you ablating the cylinder, it's going to get thinner and thinner. So
Yes.
at some point, there's nothing left. Right?
Mhm.
So is your design that at the end of the laser pulse, there's nothing left, or what?
It's not really nothing left because we can still see the strong density there, right?
Right.
In
So
the
you have some
simulation.
material left.
Yeah, we still have some material left. But if it's too thick, one, will it be able to penetrate through all that material, the laser beam? Here, I only give it to 4 grid cells in the simulation. I don't know how it will be in the reality. That's one concern.
So here in PERSEUS simulation, you have no laser package. So what you do is you deposit energy to a layer of material.
Mm-hmm.
So you're saying if it's thicker, but you deposit on the same thickness of layer,
Yes.
what would be the problem?
There's an exponential decay to give you the idea of that term. It's a power density multiplied, and then an exponential factor that lets it decay over 4 grid cells of this thickness, over this thickness. If it's too thick, that energy will still be given to the first one. So you're right that the other layer, that is the thicker part, will not be really get affected by that. It could just avoid that material to be blown up outside, and that would increase the densities further inside. So
okay, so I guess it's simpler just see the foil.
Yeah.
So let's say my laser is shining on the surface.
Yes.
You're saying that the energy
Excellent.
profile is exponential profile.
Mhm.
So this material will then expand.
yes,
So what's going on?
my grid. I'm giving it. I'm recalling that term. It's still over. It's not exactly the same. As the thickness gets larger, although the grids. The grid foil thickness term is still related to the thickness of the foil term. I scale it with it.
What if you just fix the exponential within the fringe? But let's say just make.
I see what you mean.
They,
Yeah.
they don't scale this. So the laser basically does not touch these parts of the material.
But then it would still be an obstacle for the blown up material, right?
Right, so your blown off material will just go that way.
No, but it's actually moving this way too.
So
The high density
you will
material
launch a
moves this
shock
way.
going this way, yes.
So it will be harder for it to move that. So it would, even if I don't scale it, that would still mean higher densities, and I don't like that.
Right, but your B2 compression is happening here.
Yes.
So these are low density. So here you launch a shock, you compress it to its higher density, but it's not where you care about the B2.
Yes, but then this this blown up material that is of high density and is moving upwards.
Oh,
obstacle, it needs to carry it with it.
yes, I guess what I'm trying to say is you're not blowing that off. It's inside the material. You're just launching a shock wave. So imagine this is a really gigantic piece of material. When you shine laser here, you will launch the shock wave going to the left. Shock has not break out yet, so nothing is coming out of that. So there's no material coming out the other side. So the only material is coming out on this side, which you use to compress the beam.
Yes, but that will still be hard. Like, I still want this material to get out of my way, so that it doesn't impact the densities here, right?
So you actually want to blow out.
Yes.
Blow up the cylinder.
Yeah. The more I blow off, the better for me, so that the densities will be less here. So even if I didn't scale the grid foil thickness with the foil thickness, it would still be of concern to me if it's really thick, because then it would avoid that material, that blown up material, to blow the rest of the material from its way. And they could stay here on my way, and I don't want that.
I see. So you're saying this is like a rocket effect?
Yes, it's like a rocket effect.
A bigger rocket.
Yes.
If you have a bigger rocket, the rocket does not move, it stays there. It just put all the exhaust on your compression region. But you actually want the rocket to move away, so there are less stuff left here.
Yes.
I see. So then in your experiment, is your just cylindrical shell going to fly apart?
We expect that, but
okay.
We didn't do that yet. So it's just
right. So here you're saying, so this, as you as you have this rocket kind of a
blowing.
right, so the shell is flying apart.
Mhm.
So at some point you will tell apart the cylinder is no longer going to be a single piece of material. It will be shredded basically.
Yes.
At some point.
Yes.
But that's way after your main experiment, or that's during your experiment.
I think it will be way after because we're still interested in. It kind of depends. The time scale also depends on where we are doing the experiment. For EP, it's delayed because we have less beams. So we are looking at the 10 nanosecond time.
10 nanosecond.
10, 11 nanosecond at later time because we have less laser energy. And now the scale here, it's still of 1 millimeter. So it takes some time for that plasma to move inwards because we're using less beams. So that's why it's delayed. But still, for everything to be blown up, that will be delayed too.
I see. I see. So you actually don't want the cylinder to touch your MyFab because otherwise, it can break the MyFab.
No, MyFabs will already be blown up. It will be very early too. Once we have it's again a very quick, strong current that passes through it. I think it's like 25 kiloamperes in that case. And that will be very early, and MyFab's coil will already be gone.
So MyFab will survive on microsecond time scale. So your target will survive on tens of nanosecond time scale.
Okay, maybe the pieces.
Right, so if you watch there's like high speed movie of MyFab, you energize it, it's gonna blow up.
Okay,
the time scale of that is microsecond.
Okay.
So during your laser experiment, the coils will still be there. They don't get affected yet on tens of nanoseconds. But during the tens of nanoseconds, your cylinder will blow out. Is that what can happen?
Okay, I see your point. Because yes, I saw that movie. It's microsecond. So you're right. In that case, I don't think. Yes, then it might really impact the densities. So that could be some type of worry. But the MyFab's coil is already far away from it. The radius for it is like 1.5 millimeter, and at 10 nanoseconds, the radius hardly reaches that point. So MyFab's coil will probably be blown off with it at the time of the material will reach that length already. There will be also some glue. They will already be interacting with each other. They are tied together, be put together. So at 10 nanoseconds, the point of our interest, I'm thinking out loud right now. This blown off material is already touching the MyFab's coil. But it doesn't impact the rest of it because that's already the time that we are measuring. So I don't think it will interrupt anything in that case.
I guess my question really is when you make the target, right? So people can wrap their MyFab around the plastic.
Yes.
Why don't you use that plastic to do the compression? Why do you need a separate cylindrical target? So the MyFab itself is wrapped around a piece of plastic cylinder already. Why couldn't you shoot the inside of the MyFab?
We thought about that, but one we need this. It's better if we can control the thickness of that material. So it's kind of being the same thing. It's just we're saying we are giving a shorter radius, and we are also controlling the thickness better. I think it comes to the same thing. We are already thinking about that.
Okay. And so, by the way, how do you hold your targets?
That's I think the target will be connected to MyFabs, and that will already hold it from the.
That's one piece. So the cylinder is glued to the MyFab.
Yeah, that's just one piece and one thing.
There's one thing holding the MyFab. So nice.
So that's the first day, but as I said, there are open questions for that because when we're using proton radiography axially too, that's one challenge. We might change the plans for that.
I have another question. So what limits the height of the cylinder?
That's a good question. I think I chose that height. Two things. One, I wanted to make it similar to what other people use, so that we have knowledge about it, and because I only do 2D simulation for that before. And the second one is because I wanted to make sure we can start with 50 Tesla, which meant the solenoid is more of a concern here, and I needed to make sure the solenoid can give that with the separation between them that I need. So the solenoid design actually decided on the height of the target.
Also, you have your laser illumination from one side only. The laser has a finite slot size.
Yes.
So if you are saying there's longer than that, you're not compressing field there.
Yeah.
Even minus half cylinder.
That's why we are talking about that with vector field dimensions, right? Now there's another method design, and it's actually a little bit bigger in radius, but you can directly use that because it's shorter, and you have like some right coils around.
I see. How large is your laser spot?
It depends on what you use there for the laser. This is right now something SG8.
So
Play.
it's 800 micron.
Yes.
Oh.
We can play with that.
So-
Not finally.
So the question is, do you want a larger spot or
I think that's a good question. I think I would prefer uniformity over lighting the laser energy, so larger spots.
you want a more uniform? And also that gives you a longer path like proton.
Mhm.
I see. Okay.
And the other step after that EP shot will be to have that on omega for kilotesla strength this time. And that gets even more complicated because when I showed you this, but this image gets really warped and so hard to understand when we carry it to kilotesla. So in that case, what we propose is we use again 20 beams for the cylindrical target with the solenoid, but we use, in that case, we don't have a short pulse beam at omega, so 40 of those beams are directed to the dihelium-3 filled backbiter capsule, which gets an fusion reaction to generate the protons that we need, and those protons are again directed inwards. But this time we couple this experimental setup with some Thomson scattering measurement with a 4 mega probe beam along the axis to see if the densities, because then we couple the measurements with the density measurements, because as I said, measuring kilotesla is hard, and there's still so much happening inside the target. Although we say it's subcritical, it's still a question mark. That's why we want to maybe probe earlier times in the experiment and then scale it, comparing it to the simulations. So if the Thomson scattering beam can pass through it, and if we get a significant signal during the shot day, then it means that that's a good time to probe also with proton radiography. But if that doesn't work, then it means that proton radiography won't work too. That's why we couple it together. And
Could you say again, why wouldn't the proton work if the warming up something will work?
Because protons are, this will be already complicated, but the 4 omega probe beam, during the shot day, we can get immediate feedback from it.
Oh, I see, because they need to process the proton radiography.
Yes, and it takes some etching time and so on. So in order to get immediate feedback and to say that, okay, that data is significant, can be interpreted, that's why we couple it with Thomson scattering to tell the time that we are looking at, because earlier times will be of less density, okay, less magnetic field too, but if we can measure that like less magnetic field at that time and compare to the simulations, we could get also an idea about the later time magnetic field strength.
And actually, at kilotesla, the Thomson spectrum itself was showing magnetization effects. You could measure magnetic field from Thomson itself.
In that case, I think we need to couple it to another diagnostic that I do remember talking about it, that it does not really work, and people did try to do that. What was it? Because yes, you're right, Thomson scattering could be coupled, but we need to couple it to another measurement, and I'm trying to remember it. Was it interference? Yeah, there's another diagnostic that we need to use, and I know it doesn't work, so that's why we do it.
So next April, we have another shot they're doing magnetized Thomson scattering. We're only going to have 100. But the expectation is that we have this Thomson electron feature, ion feature. It's like the loading is 0. But once you magnetize, you will have these cyclotron features on top of these. So the spacing of the cyclotron feature, roughly speaking, is C. So if you resolve these small peaks, you can actually read off the magnetic fields just from the Thomson itself.
I have a note. Me find this. Yes, the interferometry would be a problem in that case because we need
Interferometry. think there's no interferometry on omega 60. There's only interferometry on EP.
Yes. And I took a note of a problem with an interferometry.
What's the problem with interferometry?
I think it's a technical hardware problem. And we need to, I don't know. But I remember talking to someone about that. And yeah, they're being a problem. So that's why still proton radiography is in hand. But we can get help from the still for the future, the high Raday constant, the Faraday rotation. And
So here you're just cutting a hole on the wall.
to access the center.
Okay.
Because we are interested in the center.
Uh-huh.
And we can collect back the beam from there.
So you're just gonna look between the Magnetized coils.
That's really. What did you? We are still accessing that.
Yeah, so usually the Magnetized coils, they would entirely block everything. So it's a very tightly wrapped coil, like, I don't know.
Yeah.
It's like you just tightly wrap it. But now you're saying you wanted to see the times and actually leave a gap.
Yes.
in between.
Yes,
Okay.
that's what determines also the height.
I see. I see.
So that's the next step. That will be the next step. And I have some, again, simulations agreeing with the earlier ones, and also 3D simulations agree on the magnetic field compression mechanism. But these were only for the proposal, and they were of low resolution. So in that case, it's just, and there are so many computational instabilities there too. And just to see that they agree on the magnetic field compression mechanism. And there's some further work and some slides that I hid from you actually, because I have some results that I will not mention this. Now, further work is more interested in the sample, because until now I didn't simulate the sample at all, and I cannot simulate it with an MHD code already. But what we can look further into is, because we have really strong magnetic field gradients around the sample location, those strong magnetic field gradients would be related to the currents there, and those currents could relate to the ohmic heating of the sample. And that's another actually way to create warmness matter sample, because you can just heat it. And I have some results on my end, but not final results. But I'm optimistic that that in 1D simulations I do, the sample can be heated to the temperatures needed to have warmness matter, which is like 1 eV, through that magnetic field gradient, which implies that we don't even need a heating beam and the subcritical density plasma to create the sample itself, which helps further with studying the warmness matter sample. But in that case, you might say, do you even need that setup? And do you even need the open geometry? And that I would then reply that one, people in magnetized HGDP community can still benefit from that. It's still a good approach. And two, if you want to diagnose the sample further, it could still be helpful. And also for measuring the magnetic field strength, that will be of advantage. So there would be still advantages of the current design, but we might need to change the geometry a little bit in that case to get help from that ohmic heating that will be present on the sample.
Can you elaborate on why strong B field gradients cause ohmic heating? What's the basic?
Because ohmic heating is just heating with the currents, right? So, and the strong magnetic field gradients will generate those currents right around the sample too. As I showed here, these gradients are significant. And once we get to kilotesla, even more important. So I do have some stuff for that, but I don't have the final answer. That's why I didn't include the simulations on my slides. But another active question is, again, as I said, we're thinking of Faraday rotation and coupling it with a high Raday constant. And the other one that I was thinking is maybe instead of protons, I don't think we will be able to do that, but using a heavier ion could help, because in kilotesla, those protons are moving too much, and that's why the wrapping in the synthetic proton radiography is hard to see. But if we were to use a heavier ion, it would not be as warped, and it would be easier to interpret. But that's like a new diagnostic, so I don't think LLE people are happy with that. So, but just to think, because of how it is. I like the idea better, but I don't think they will help me with that. So with that, today I talked about why we're interested in magnetized warm-dense matter and how it's relevant to both astrophysics and fusion, and why we couldn't have any experiment on that before because of the way it needs an open geometry with subcritical density plasma, along with really strong magnetic fields reaching kilotesla, and how the alternative design we have could incorporate both of them. And then I showed you the MHD simulation results in PERSEUS, giving us an optimistic optimistic approach to start this experimental campaign. And then I mentioned the experiment proposals and the coming shut day, how we plan to measure the magnetic field. And that was about it. Thank you for listening, and thanks for having me here. I don't know if there are any questions on Zoom.
You said like both plasma